this JWebinar, it's called Time Series Observations. And we wanted to, of course, explain first what do we mean when we talk about time series observations. So what are time series observations? And here, we're just defining them as any multi-integration exposure aiming to constrain time variable phenomena. We mean every word out of this sentence. And one of the things that we are kind of assuming is that you're a little bit familiar with the JWST jargon, but just in case you're not, here's a little bit of refresher on what we want for you to know beforehand once we go into the TSO notebooks. So this sentence here says any multi-integration exposure. So an integration, as some of you folks might know, it's composed in the JWST detector read modes as a set of groups. So what the JWST detectors do is that they read up the ramp. So they start with a reset frame, and then they start collecting photons up the ramp, so they don't shut down during the integration, at least in TSOs typically. So they go up, just capturing photons in different groups. So every group, it's going to have more and more and more electrons and detector in the detector. And then a set of groups defines what we call an integration. And then in TSOs, typically, you take several integrations, several of these groups. Groups typically, for example, can take all the way from in the order of seconds. And integrations, this is the same thing, it's the same order. And then a set of integrations, several integrations which you typically have in TSO exposures, it's what we call an exposure. And this is the very basic nomenclature that we really want for you to understand beforehand, before jumping into the notebooks. So probably you're all familiar with it. Some of you proposed for JWST proposals. Some of you have been aware from JDocs. But if not, I mean, this is the very fast refresher that we had for you. Now, TSOs span a wide array of scientific cases in JWST. And of course, I see a lot of names here that are linked with transiting exoplanets, which is most of the general observer proposals. But that's not the only scientific case, actually. So there's a ton of other scientific cases in cycle 1, at least, including brown dwarf variability, accretion variability, both at galaxy scale and both at planetary or protoplanetary scale, and even solar system occultations. And this is just the sample from the first cycle of observations. I'm pretty sure as we go in the next cycles, people are going to figure out new ways of using TSOs for their own science. So it's a very broad, it has a very broad scientific use cases. In terms of what instruments can perform TSOs, we're going to highlight 4 here that are on board of JWST: NIRCan, MIRI, NIRSpec, and NIRIS. 4 of them can do time series observations, and they can do both photometry and spectroscopy. So that's the very important part. Another very important detail, which I'm showing here in the right panel, is that each of the instruments has their own little space within JWST. They have some of them have similar detectors, but they're not sharing the detectors across instruments. Across instruments, between different instruments. So we're going to focus in this TSO webinar, we're going to focus in particular in spectroscopy. And the reason is basically that if you learn how to use spectroscopy, it's easier to translate that information to photometry, but the other way around is not that easy. So that's why we're focusing here in spectroscopy, also because we have a limited time. Of course, we will love to spend here hours and hours with you, but we have limited time in our agendas, all of us, including yourselves. Now, the different instruments span different wavelength ranges and also span different resolutions. And I'm going to be spending a little bit of, sharing with you, in case, again, a refresher on the wavelength ranges of the different instruments. So first up here in this slide, it's NIRSpec. So NIRSpec has the quite famous or quite popular in cycle 1 prism mode that allows you to cover all the way from 0.6 to 5 microns at low resolution in one shot. And in case you wanted to go to higher resolution, it has these other modes: G140, M and H, the medium and high resolution, G235, H, and G395, M and H, again, medium and high resolution, in case you have bright targets. So, one of the details of NIRSpec prism, of course, is that it saturates at relatively bright, for relatively bright targets. So then you can choose the other modes as well if you go to writer objects. Next up, we have Nearest. Nearest has this one mode, the SOS mode, which allows you to gather all the way from 0.6 to almost 3 microns. It's composed of 3 orders that you can extract spectra from, and we're going to hear all about that in a notebook in a bit. And it's typically very good for very bright objects, so it has the bright limits are very good. Same case go for NearCam. NearCam is also very good for bright objects, and it covers a complementary wavelength to what Nearest does with these 2 modes, F322W2 and F444W, that allows you to capture all the way from 2.5 all the way up to 5 microns. So as you see, these are very complementary, and this portion, these 3 instruments that I'm putting here, NearSpec, Nearest, and NearCam, is what we in the JWST jargon typically refer to the near-infrared instruments. 5 microns might not be your near-infrared, but it's up to you to decide. But that's the nomenclature that we use here. And we use this nomenclature because we have another beautiful instrument on board of JWST, which is MIRI, right? MIRI allows you to go to the near-infrared. To me, this is the D-infrared, right? All the way from 5 microns, even up to 28 microns with some modes. But the main modes that people are using during cycle 1 is LRS, the low resolution spectrograph, that allows you to go all the way from 5 to almost 12 microns. And Sarah is going to be showing you some simulated data on LRS. So you'll have the best of both worlds, the near infrared and the infrared. And there's also a mode for MIRI that uses an integral field unit, actually, the medium resolution spectrograph that has these 4 channels. We're not going to be touching on that here. There's a calibration proposal that I'm going to mention in a little bit that's going to try to explore how this works for TSOs. But that's also a very interesting mode to have in mind for future cycles. That, again, we won't cover here, but keep in touch with the JWST documentation. That definitely information is going to be there. One very important thing that we have to say here is that the detectors that the near-infrared instruments use, NearSpec, Nearest, and NearCam on top, and the detectors that MIRI uses are different, and therefore the information that you will learn in the near-infrared detectors is not the same or cannot be easily translated to what you will learn in the infrared detectors that MIRI uses. So just be aware that these are kind of 2 different beasts that you have to take care of and that you have to have in mind before jumping right ahead into the data. Hence, why we're here showing you about these 2 sides of the story for Webb. Before jumping right away into the JWebbinar, we wanted to let you know that there's going to be there's already some interesting data sets out there, simulated data sets, for you to play with. So we entitled this section, TSO data sets to be on the lookout for. So again, as I was telling you just now, already the Transiting Exoplanet early release science program members have compiled simulated JWST time series observations datasets for all instruments. So you can go to this webpage here. So this dataset that they released, it was released during a pre-launch hackathon that they had in the summer, and in which there's these 3 datasets for the 3 different instruments. So there's a transit all focused on WASP-43b. There's a Nearest SOS transit that we're going to use in a notebook in a bit. There's a NearCam Grism transit, a NearSpec POTS transit, and a MIRI LRS partial phase curve for WASP-43b. So you can already have a ton of fun with this simulated data, and we're going to be showing you a little bit of that fun in this JWebbinar. Now, another thing to have an eye on is that we're going to be commissioning JWST, and there's a handful of TSO observations that we're going to be making that once commissioning ends and everything checks out with commissioning analysis, then it's going to be released to the public. So you're going to be able to use that. So as you know from launch, there's going to be a 6-month commissioning phase where there's not going to be an official data release. And then after that 6-month period is over, then there's going to be a big release of the first science observations that JWST is going to make, the early release observations. And then with that, there's going to also be like a release of this commissioning data, and then that's when cycle 1 starts. And during commissioning, again, these programs are public, by the way. You can look at them up in Google. Nearest SOS, for instance, is going to be looking at a transit of Nhat P14b, and it's also going to be looking at the time series observation of a standard star. So that's a data set that you might be able to get a hand on. Near congruism, we'll be looking at an eclipsing binary to test the TSO capabilities. And MIRI LRS and near spec bots, both will be looking at a flux standard with a TSO for like an hour or two. So that's also a very interesting data set to have if you want like an early start with a data set. That's very nice. But the real, I would say, data set challenging all the interesting modes, at least for transiting exoplanet science, is the ones that the transiting exoplanet community ERS programs are going to be obtaining. So this data set will be the first scientific data set exploring TSOs with all modes, at least for transiting exoplanet science. They're going to be observing, a transit of a planet, an eclipse of a planet, and a complete phase curve of a planet. So here's some of the targets, the nominal targets. There might be changes with this, with the launch date now. So they're going to be looking at this transit with 3 different instruments: near SOS, near congruism, and near spec bots, like 8 hours each. So that's a huge data set, all the way from 6 to 5 microns. Then they're going to be looking at this eclipse of WASP 18b with near SOS, so testing the bright object capabilities of the instrument. And at the right, you can see this phase curve, which the nominal target of WASP 43b, it's likely that's going to change, but it's going to be observing all the way from 5 to 12 microns with MIRI LRS. Now, that's not the only data set that you should be paying attention to during cycle 1. There's also many GEO programs, like Accept the General Observer Proposals, that have 0 proprietary periods. So those are data sets that you can actually go and download the data and start checking out how the TSOs work. There's a full list here, but I'm just highlighting here some of them. Like I was just telling you before, there's a time series calibration of mean resolution spectroscopy with MIRI, the MRS mode, that Greg Deming is leading. And another example of a big project doing a ton of transiting exoplanet science is this program led by Natasha Batalha and Joanna Teske. It's a huge 140-hour near-spec bots exploration of various transiting exoplanets that again has 0 proprietary periods, so you can get a head start on analyzing TSO data. With that said, so now you know that there's going to be like a ton of data sets, and the next question is, how do I get started reducing this data? And this is where we're going to take you during this JWebbinar. But before that, we wanted to give you like a big picture of how the general flow of the SDSCI JWST TSO pipeline and the data reduction works, which again, we're going to take you step by step, but this is the general picture. The general picture of the pipeline, so first of all, yes, there is a pipeline. And this pipeline is actually, and we're going to show you how to use it, and this pipeline is divided into what we call stages, which are 3 in particular, and these ones do like very big things on the data to produce you like usable TSO products. And each stage actually has certain steps for which you go one by one in order to generate the end product of a given stage. The very first stage, stage 1, is detector processing. And how this works is that you get the uncalibrated data in the left here. I called it here stage 0, in which you have the uncalibrated data, so you have all the detector effects on top. And then after this stage 1 part of the pipeline, after many steps, you remove a ton of these detector effects. And you can see that from the left to the right is much cleaner. The right one looks much cleaner around the spectrum. So this is the spectrum of near SOS, where you see at least 2 orders. So the first order is the top one, and the bottom one is the second order. Then you have stage 2. So stage 2 is spectroscopic processing. So this actually gets you an extracted spectrum. So, counts or flux, depending on what you want, over wavelength. So this is the case for order 1 and order 2 here. So you can see the wavelength ranges that they cover. Order 2 from 0.6 to almost 1 micron, and order 1 all the way from 1 to almost 3 microns. And then we have stage 3 that actually produces to you a white light curve that you can actually explore and fit and play with.